Hi friends, myself Naga S. Siramat. In the previous videos, we discussed what is microprocessor, what is the history of microprocessor, then addressing modes, and also we discussed how to calculate the physical address of the memory location. In this video, I'm going to explain the instruction set of microprocessor, which are the instructions will be available under microprocessor. The main objective of this video is data transfer instructions. Which are the data transfer instructions? How those instructions will works that we have to study. And also arithmetic instructions. The first we'll look on data transfer instructions. The data transfer instructions are nothing but transferring the data from one location to another location. Here we are transferring the data from source operand to the destination operand. What is this source operand and destination operand? See, we have the format for use of instructions. So that is opcode, then destination operand and source operand in case of microprocessor. The opcode, as the name indicates, it is operational code. OP stands for operational code. It tells to do the operation. That is the meaning of opcode. Operation code. Which operation we have to do. That is the meaning of opcode. Destination operand, comma source operand. Here, suppose if we are using move instruction, we have to transfer the data from the source operand to the destination operand. That is the meaning of source and destination operand. Source is one location, another location is destination. So suppose if you want to transfer the data from source operand to destination operand, then we have to use instruction MOV, that is move. So example here MOV. So the format of this instruction is MOV. This is opcode, it stands for MOV, and destination operand, comma source operand. The main function of this MOV instruction is it transfer the data from source operand to destination operand. So that is the meaning of data transfer instructions. So if you see the condition of this move instruction, here the source operand may be byte or word of data, and destination operand also may be byte or word of data. Byte in the sense 8 bit of data, word in the sense 16 bit of data, and source operand may be register or memory location. Destination operand also may be register or memory location, but both at a time, source operand and destination operand, both at a time should not be memory location. Either it may be register or memory location, either register or memory location, but both at a time we can't use source operand as well as destination operand as a memory locations. So these are the conditions for use of move instruction, and it doesn't affect any flag registers. So in the previous video we discussed about flag registers. So this, if you execute this instruction move, it won't affect any flag registers. If you see the examples of move instruction, move CX, 037AH. See here, move is an opcode here. CX is the destination operand register, and source operand is an immediate data. We have the data 037AH. This data we are transferring to the CX register. That is the function done by move instruction. It moves the data of 037AH to the CX. CX is acts as a destination operand, and this value is in source operand. So after execution of this instruction, we'll get CX value is loaded as 037AH. So another example, move BL comma in the bracket 437AH. See here in this example, the destination operand is register, the source operand is memory location. In this, what is the memory location address? 437AH. In this address, we have some data. That data is transferred to BL register. That is the meaning of move BL comma in the bracket 437AH. The next instruction is exchange, XCHG. The opcode of exchange is XCHG. The format of this instruction is XCHG destination operand comma source operand. So what it does, it just exchanges the data between source operand and destination operand. Whatever data available in source, that goes to destination, and whatever data available in the destination operand, that goes to source operand. Just it is an exchange the data between the source and destination operand. Then what are the conditions for this? So whatever we check conditions for the move instruction, almost same conditions will apply for exchange instruction also. The source operand may be register or memory location. Destination operand may be register or memory location. Both at a time, source and destination operand should not be memory locations. And this instruction also doesn't affect any flag registers. If you see the example of exchange instructions, see here exchange AX comma DX. So after execution of this instruction, whatever data is available in DX that goes to AX, and whatever data is available in AX that goes to DX register. So here AX and DX both are 16-bit registers. So you have to check while using the instructions, both should be same size. If the DX is 16-bit, another destination operand also register should also 16-bit register AX and DX. So another example, exchange BL comma CS. So here both are registers. So whatever data is available in CS that goes to BL, whatever data is available in BL that goes to CH register after execution of this exchange instruction. So another example for data transfer is LEA instruction. LEA stands for load effective address. It loads the effective address of the source operand location to the specified register. So whatever you have the address, that address data, whatever data is available in that address, all those data will be specified in the another specified register in the destination operand. That is the meaning of LEA. It loads effective address of this location to the specified register. So then what it does? So here whatever data is available in the memory address, all the data will be loaded into the register. So that is the meaning of LEA. You can use 16-bit registers. LEA does not affect any flag registers. If you see the example, I have the memory location num. The memory location name I given as NUM num. So in that I have the byte of data. So I specified DB defined byte. I have 4 data 11H, 12H, 13H, 14H. See all these data I want to load in the some register location. So for that we have to use LEA instruction. How to specify? See here LEA SI comma num. So in this num is the memory location. So in that memory location I have all this data. That data I am representing in the location of register is SI. So now all these data are represented by SI location, SI register. So the use of doing like this is you can select particular data in that location, or you can increment the location values or decrement the location values. So that is the purpose we are using LEA instruction. It loads effective address of num to the SI. So why it is SI here? It is 16-bit, and always num having that address is 16-bit address. So that address is loaded into the SI location. You can use any register here instead of SI also. You can use DX register. You can use DI register. So like that we can use different 16-bit registers in the destination operand. That is LEA. So here you can see we consider num. The num address is represented as 2000H. In that 2000H I have the data is 11. Next location 2001, 12, 2002, 2003. Just to make correction here. This is 2000, 2001, 2002, 2003. So in that location I have data 11H, 12H, 13H, 14H. All this data I am pointing now SI location. This is the representation of LEA. Now this address is represented by SI. Next is LDS. As the name indicates, it loads the data segment address. LDS stands for load data segment address. LDS, the format is LDS register comma memory address. It loads the first 16-bit address to the specified register. Next 16-bit address of data will be loaded into the DS register. The meaning of this LDS is in the memory address I have the data. In that data, first 16-bit data will be loaded into the specified register. Next 16-bit data load into the data segment register. You can see here. You can see the example LDS BX comma in the bracket 4326. See here this 4326 within the bracket, so it is represented as memory address. In this address I have data. In that data, first 16-bit data will be loaded in BX register. Next 16-bit data will be loaded into the data segment register. That is the meaning of LDS here. This instruction loads new values into the specified register and into the DS register. From 2 memory locations is copied into the specified register. So first 2 memory locations. Then another word, the next 2 memory locations will be loaded into the DS register. That is the meaning. So you can see here I have the address 4326H to BL content of 4327H. That is first location, second location. So that will be loaded in BX register, lower BL, higher BH. Next, another two memory location, copy content and displacement, that is after 27, 28 and 29. Those two values will be loaded in the DS register. That is the meaning of LDS. See here 4326S, I have 11, 27, I have 12H, 28H, 13H, 29H, 14H. So here 11 and 12, 16-bit data. 11 and 12 will be loaded in BX. 13 and 14 will be loaded in DS register. That is the meaning of this instruction. Next is LES. It is same as previous one. Only instead of data segment, it is extra segment. Load extra segment address. It loads the first 16-bit data in the specified register, next 16-bit data in the ES register. That is the meaning of LES instruction. See here example, LES BX comma 789AH. So in this 789AH, I have the data 11, 12, 13 and 14. First 16-bit 11 and 12. So it is a 16-bit data that will be loaded in BX register. Next 13 and 14 will be loaded in extra segment register. So these are all data transfer instructions. Now switch on to the arithmetic instructions. So very simple arithmetic instructions. First one is ADD/ADC, addition with carry. ADD stands for addition, ADC stands for addition with carry, C stands for carry. You can see first one, add. The format of add instruction is ADD destination comma source. So ADD is an opcode, destination operand and source operand. So then how it works? It adds the source value with destination and result will be stored in destination operand. The function of ADD instruction is whatever we have source value, that value will be added with destination value and result will be stored in destination operand. Then what are the conditions for this? The source may be register or memory location. Destination may be register or memory location. Both cannot be the memory locations. These are the conditions for add instructions. If you see the examples, add AL comma 74H. What happens? Here 74H is an immediate data. That data will be added with AL register value and result will be stored in AL. You can see here AL equals to AL plus 74. 74 will be added with AL value and result will be stored in destination, that is AL register. Then in 16-bit example, add DX comma BX. The BX value will be added with DX and result will be stored in DX. Then ADC, another is ADC, add with carry. What it does, it adds source value with destination and also the previous carry will be added with the destination. So ADC CL comma BL, BL value add with CL and also add with previous carry and result will be stored in CL register here. Then SUB SBB, subtraction instruction. SUB stands for subtraction, SBB stands for subtraction with borrow. The format is SUB destination comma source. What it does, it subtracts the source value from the destination and result will be stored in destination operand. Again conditions are same, source may be register or memory location, destination may be register or memory location. Both cannot be the memory locations. If you see the examples, SUB CX comma BX, the BX value subtracted by CX and result will be stored in CX. So here CX equals to CX minus BX. If you use SBB, subtraction with borrow, what happens? The AL value subtracted by CH and also the previous borrow will be subtracted from the CH and result will be stored in CH. So we can write the expression CH equals to CH minus AL minus previous carry. Then multiplication instruction, MUL. So MUL source. So here the format of the MUL instruction contains only source operand, destination operand done by accumulator register. So here if you want to multiply the two values, the source value you can represent with some registers and the destination value always should be represented by accumulator register. So what happens, the source value will be multiplied by accumulator and result will be stored in accumulator registers. You can see the example for this, then you can easily understand. Here, example MUL BH. What happens? This BH register value multiplied with accumulator value. So you can see here the BH value multiplied by AL and result will be stored in AX register. If you are multiplying two 8-bit register, result will be stored in 16-bit register, that is of accumulator AX. Suppose if you are multiplying with 16-bit register, for example MUL CX, what happens here? CX is multiplied with AX and result will be stored in two registers DX as well as AX. That is, in AX lower 16-bit will be load, in DX higher 16-bit will be load. That's what it is written here. When word is multiplied by the content of AX with the another register, then result will be stored in AX and DX. Lower 16-bit in AX, higher 16-bit in DX. It is in case of 16-bit value. Suppose you are multiplying two 8-bit value with accumulator, the result will only stored in AX register. Then IMUL. Suppose if you want to multiply signed numbers, then we have to use instruction IMUL. For signed numbers, if we are using IMUL instruction. Suppose one value is positive, another value is negative. In that case, if you want to multiply, you can use IMUL instruction. Again, the operation is same, only just is sign extend operation. So you can see the example. IMUL BH. The BH will be multiplied with accumulator AL and result will be stored in AX. IMUL BX. The BX will be multiplied with AX register and result will be stored in AX as well as DX. DX contains higher 16-bit, AX contains lower 16-bit. Then division instruction, DIV. So again the format of DIV is DIV source. Destination operand is accumulator here. So just we have to represent format as DIV source. So here if you want to divide the number one by another one. So the source operand is maybe BX register or BL register or CXCL, like that you can use. And destination operand, that is accumulator register, you have to use AL. Suppose if you want to divide 16-bit by 8-bit, so 8-bit number should be in source register. So we are dividing accumulator by another source operand. You can see the example here. If you divide 16-bit by 8-bit, so then result will be stored in AX. How it will be stored in AX? You can see here. The divisor can be in register or memory location. After the division, AL will contains 8-bit quotient and AH will contain 8-bit remainder. If you are dividing 16-bit, that is AX by BL register, for example. After dividing, the result will be stored in AX. In AX, lower bit 8-bit, that is AL register contains quotient value and AH contains remainder value. That is in case of 16 by 8-bit. If you are dividing 32-bit by 16-bit number, then result will be stored in AX as well as DX. AX contains quotient, DX contains remainder part. You can see the example here. DIV BL. I am dividing 16-bit by 8-bit. So in that case, result will be stored in AX. How? AL contains quotient, AH contains remainder. AL contains quotient, AH contains remainder. If you are dividing 32-bit number by 16-bit number, then result will be stored in AX as well as DX. AX contains quotient, DX contains remainder. Then IDIV. This is with respect to sign number. Suppose if you want to divide negative number by positive or negative number by negative number, then you have to use IDIV instruction. It is same as DIV instruction, only sign extend. You can see the examples here. IDIV is IDIV BL. It divides accumulator by BL register and result will be stored in AX. This is also IDIV, just make correction. IDIV by IDIV CX. So quotient in AX and remainder in DX registers. Next, increment instruction, INC. So just it adds one value to the data or it adds one value to the memory location. Suppose if you want to increment memory location, you will add one for the your memory location address, or if you want to increment the value, then it adds the 1 value to the value. So that is added by 1. So you can see the format of this instruction. Format is INC destination. Here destination may be register or memory location. If you use register, the register value is incremented by 1, that is add by 1. If you use memory location, the memory location address will be incremented by 1. INC BL, that is BL plus 1, register value is incremented by 1. Suppose you have BL value earlier it is 4, now plus 1 it is 5. So after execution of increment BL, you will get the BL value is 5 like that. INC CX, so CX is earlier is 16 plus 1, then it will be 17. Like that it will be incremented. If you use memory location address will be incremented by 1. Then another simple instruction is decrement. Here it's subtracted by 1, either register or memory location. Examples, format, decrement destination, DEC destination. So here destination may be register or memory locations. You can see the example DEC CL. So CL register value is decremented by 1, CL minus 1, and result will be stored in CL only. And DEC BP, the BP register is decremented by 1 and result will be stored in BP only. So like that it will execute. Thank you for watching this video. If you like, please share and also subscribe. Thank you once again.